Welcome back, everyone. The first session on Thursday. It's my great pleasure to introduce Siva Athreya. He will be talking about Graphon dynamics, where the dynamics actually change over time. A very exciting topic. Please go ahead, Siva.
Thank you very much. Charles, can you hear me? Can have my mask on. Thank you very much for inviting me for this meeting, and it's a pleasure observing all the talks. This is work with Frank and Adrian, who are in the audience. Any questions can be directed to them.
But do use the microphone.
This is kind of an investigation in progress. So there's developments I'll report on. Some have been proven, some we think are true, some which are false but we think are true. So the broad idea is I will not go into the basics of dense graph theory because I think everybody is familiar. So what we wanted was a dynamics on Graphon space that came from a discrete system. That's the goal. So I'll write the goal on the board so that the goal is clear. So we all know that you have a Graphon. So I'll call it H. H is Frank's notation, unlike Adrian's kappa. So I know I can these are well-defined functions. I can define some dynamics here. What we wanted was, in dense graphs, we know that there's always a finite graph. Again? Oh, my Graphons moving around in time. But what I want to do is I want to chase them with all the finite graphs, any sort of system that is coupled in some way with the graph. So these typically would weakly converge for every fixed t. But as the Graphon moves, as the graphs move at level n, I would like them to replicate the dynamics. You can think of various things you want to do with this. Some people turn edges on and off.
Is H iterative?
Yeah, as of now, everything's up. So yeah, but I want a diffusion finally. So this dynamics in networks is quite well studied in various forms, in various settings. But I think the dense graph is in its early stages. That's fair to say, I think. So for example, if you look at many applications in biology and even social networks, the network is changing all the time, and people are trying to understand what's going on with the network. So during the pandemic, I had the opportunity actually to work with an agent-based model, transmitting infections across. So I'll discuss 3 motivation examples for our study. This is not a motivation, but so a bunch of collaborators of mine built a simulator from this is from Ferguson's model. Ferguson is a person in, I think, Imperial. He had a simulator for Thailand, and he can simulate Thailand and tell you how the infection will spread in Thailand. So like that, so my collaborators built a simulator for Bangalore, and so I'm running it. I think it's taking up their power and their server. But yeah, so you could specify many things like from mean incubation time of the disease to recovery time to how many hospital stays, ICU stays, and how many households there are, and so on and so forth. And they're all governed by a sparse graph system. And you allow the virus to spread, and you can play the video game and see what's going on. You can check when your threshold hospital is going to be reached, depending on how the biology works. But again, of course, I have populated the city with 100,000, so that's 2 less. Bangalore is 12 million. And the moment you jack it up more than 3 million, the simulation stalls. So you have to be careful. That's a whole new challenge out there. in terms of dense graph theory as well. At the 100,000, 500,000 level, even if a person like me writes a program, it will run. But anything more than that, the challenges get very, very complicated. You have to optimize differently. You have to locally look at it, and so on. My second motivation was Frank and Remco's early work on. So what they did was they took the configuration model. They had a random walk on it. It had a certain mixing time. Then they did some rewiring every now and then, and they slowed the walk. The walk won't see everybody. So I wanted to understand if such a scheme is possible in the dense regime. That was my initial motivation of getting into this idea of dense. And Adrian and I were playing with how to sample a dense graph, and the way you sample will affect what graphon you see in the limit and so on and so forth. So based on that motivation, I wanted to see if this could be replicated in the dense regime. I have some thoughts on that. I can discuss that at some point, but that also is not complete. So. Then recently, of course, there's sort of I don't have that. Let me see. Let me see if I can pull that out for you. So not this one. Yeah. So maybe I'll just show this. It's okay. So recently, there's sort of been sort of connections of graphons in deep networks, neural networks. It's a nice first step, I think. So what they're trying to understand is trying to provide, at least after I talked to them, I understood, not from the paper, but that they're trying to give some sort of mathematical rigorous meaning to deep learning. Okay. And they're modeling it as a gradient descent on graphon space. It's quite nice. The idea is quite nice. And it's very similar again. You look at finite graphs. That's like a matrix. So think of it as a gradient flow on Rn squared. And as n goes to infinity, if you stick with Gatto or somebody else, some of the derivative, you will get a gradient flow on the graphon space. That's quite nice. I think I've explained the work correctly. But, that's quite nice. That's a nice part of work, I think. It's beginning, I think. I think there's lots of interesting work available from this setting as well. So there are dynamics being studied around on graphs and mathematically and otherwise as well, with very, very non-trivial. So coming back to my question that I wanted to study. So you can visualize it as any dynamics, right? You take a Edersheim graph, for example. You can do your favorite dynamics. So you go to every edge, turn it off, turn it on in some way, or you can make edges appear in some way. It'll create some dynamics, but that dynamics has to stay in the limit. Typically, in dense graph theory, that's a little hard to achieve. You get a deterministic flow, but diffusion will be hard to achieve if you don't do something drastic. Because you are averaging at the level of n squared in some sense, and then if you change order n edges, you won't see it in the limit. It will just go away. The randomness will go away. Of course, this is a challenge I'll describe slowly. Crane was the first person, Harry Crane was the first person I attended. So there's a series of papers they wrote, but they used the Aldous-Huer theory to work with graphons, not sampling from the graphon with endpoints and giving labels. They used the exchangeable array. Of course, now it's well known that from Janssen and Diaconis's work that the projections on the graphon space induce from Aldous-Huer theory, exchangeable random variables, you can project on the graphon space. But what Crane produces was processes that are only of locally bounded variation. That means you can't have diffusions using that idea. Something that's a stumbling block. So when I saw this, I thought, okay, so something didn't make sense to us in some sense. But it's a very, very delicate result because they're using at every n, if you're worried about n plus 1, the graph covering in an almost sure way, then you only have to do this. But if you're only worried about the structural properties of the graph in a distribution sense, then you don't have to do this. If you're only worried about subgraph counts and other things, you don't have to do this. So you can look at Cherny's and Anton Klimovsky's survey. I'll attempt a brief survey and I'll show it here. This is the basic Aldous-Hoover theory that you can think of your graph as a graph on countable edges. The graph is given, any infinite exchangeable array graph is given by a function of this form, where f is one deterministic function available. And they're all uniform. So Crane used this object. Of course, this is built on Diaconis and Janssen's idea that, or paper, that the graphon and the exchangeable array are related by this expression. So the one-to-one correspond. You can work with either of them. But what happens is that if you work at the exchangeable array setting, you end up with processes of bounded variation only. You can't get diffusions because somehow there's too much information there. Crane showed that. But it's also a matter of taste, right? So there could be potential diffusions here, but if you project down to the graphon space, you'll only get things of bounded variation. That projection somehow sort of damages them. I'm saying it correctly. So we can't do this way. But so when Aidan and I discussed first, I mean, it's kind of sad, right? But also silly. But what if I do the following? I take my classical GNP, right, that I have, right? Okay. So I don't put P. I just put my favorite edge probability as P of T, okay. or Y of T. Yeah, go ahead. Yeah.
Microphone.
Yeah, sorry, quick question. So going back to the Aldous-Hoover thing that you showed,
yeah.
So, one more, I think. Or sorry, one more. Yeah. I mean, so suppose now these U's and etc. Suppose they're like Brownian motions or some diffusion. Yeah. Then you have Xij T's. So what happens if you do something?
The key is the projection right here. That will give you when you project down to the graphon space, you will not get diffusion. If you do that calculation. We have an example in our paper where we do exactly what he said.
I see.
If you want an adapted process to some, it'll be you know everything about the whole thing.
Okay.
You're just saying that take UI, UT, and UJ as Brownian motion and try the whole thing, right? So at the Xij level, you'll have that. But the moment you go to the graphon space as a projection, that projection map will not give you diffusion. It will force you to be Brownian variation. You're right. That's right. You can just do the calculation. But see, this like Shankar said, or even simply, you take a GNP, but put YT to be some diffusion as a connection probability. Right? So I and J are connected with probability YT. Right? The height is moving up and down like a Brownian motion or anything you want, 0, 1, and that's a diffusion. That's a well-defined diffusion. All subgraph counts will diffuse, and it's a nice diffusion. So there should be some way to do this. Right? So you just can't say there's no diffusion on graphon space. That's the simplest example you could think of, which should be achievable in some way.
So this example in particular is then not Markovian.
Correct. That's right. So
why not?
Because the
Markovian on the Aldous-Hoover.
Aldous-Hoover thing, right?
Yeah.
It's a function of f, right?
Right. The right question. So in Aldous-Hoover,
yeah,
you have your two variables x. The first two variables which I consider features,
right?
And you have the last variables which give you the random graphon,
right?
And why can't I make my random graphon Brownian? I don't introduce it via the use. I introduce it via the random graphon.
Right.
So via this last U maybe. Because they're different random variables, right?
Okay. I can come back to it. It'll still not work, I think.
It will still not work.
Because Rain has shown a theorem that says that when you project onto Graphon space, you'll only get bounded variation in this.
So wait. Assume, so we have an f of u, I don't quite, one of your u's is actually just encodes a random graph.
That's right.
So what if I make f equal to ZU,
right.
and then make U Brownian motion, then I have exactly your example.
Yeah,
so what do you mean it doesn't work? So to some extent,
I'll tell you what I mean doesn't work, in the sense that I want it coming from a system of n particles to that. A priori, I have a diffusion on space. That's not my question. I wanted to come from.
I think what this would tell us is that since this is a random graphon, and the random graphon is sort of an element of the sigma algebra at infinity, your Brownian motion has to somehow sit at the sigma algebra of infinity. So you will, in each observation, you will only see one sample from the Brownian motion, but behind the scene, God has a random graphon which is Brownian motion.
I think that's correct, but I want to get from, I think that's correct, but I can't take that God-given Brownian motion and repeat this construction from n to this one. I can't do that. I can't have a dynamics at the nth level that gives me a diffusion at the limit. That's what I'm interested in. I'm not interested in arbitrarily giving you a diffusion on the Graphon space. That I can give you for sure. Any way I want to give you. But if I want to construct from the nth level to the infinity, I can't do it that way. So I need to know the information of the whole array. I have some exciting things to say, so if I get stuck at this, let's keep going. Is it okay if you don't mind? I don't mean to be offensive. But yeah, I want to put my co-authors on the spot. So the I have till 9:40, right? So so how would you do this? So if I want, I want diffusions in the subgraph metric, right? So again, it's important. This whole thing is working on this. I want it to come from a discrete dynamics. That's the whole thing. So I want an interesting discrete dynamics that passes on as n goes to infinity to a diffusion on the graph. That's what I want. Like all of you have said, a priori you can do Aldous Hoover or yourself and construct a diffusion on this space by yourself. That's not the construction I want. I want it to come from. So what would you do? So you can see this idea that look at a fixed t, you look at G and T, look at the subgraph counts, right? So they will be of this form, the number of copies of F in Gn by the complete graph. And then as n goes to infinity, they should suitably go to some graph on h of t at time t, so every fixed t. That's our standard. And this, what are the key features in this? There's an averaging effect. You compare this to the mean by a concentration, and you work with the law of large numbers of U statistic to get the result. But in this averaging, you lose out the diffusion part if you start with the diffusion here, if you don't do it in a clever manner or a drastic manner. Because what's happening in this is a lot of averaging. So let's do our favorite stochastic block model that we have. Yeah.
So just very quick question. I know you want to continue, but if you can start with a Brownian motion, you could potentially discretize it, like make a Markov chain in time.
Yeah. So
and then infer a dynamics on here.
Correct. Yeah, you can try that. But you have to show that the subgraph counts of the induced one gives a Brownian motion on that one. So let's check that. There may be some challenges there. I'll come to it in a second. That's right. That's exactly it. Yeah. What you have to do for that is what I'll tell you. So you can't do a simple on-off mechanism at the GNT to get a diffusion of XT or something. So what I want to do was I want to do something like this, like a simple, let's say, stochastic block model, but I want this person to diffuse, let's say, on this thing. Something like I want. How do I construct a social network on n vertices to give me this? For example, keep in mind that I'm after. So I want a sequence G and T that gives me this. And the sequence should not come from YT. It comes from YT, okay, that's easy. That's like, I think it's a little tricky, but I want some interesting dynamics at the nth level that gives me a diffusion of YT. I don't want to take and sample from this YT and say, okay, I get this YT. So what we thought about it, and so our first work, we decided to do it a little differently. So if you do, like I've said, like, you know, you at some times you keep some edge active, sometimes you keep some inactive. This averaging will sort of make sure that deterministic will be, the flow will be deterministic in the limit. The randomness will not survive because so much averaging. So you have to do something drastic. So what we did was we went to population genetics and we did the following. So you have vertices 1 up to n, and you give labels for everybody, x1 n at time t, xn n at time t. Each label is 0 or 1, so each xk is so, and then all I do is I do a Moran model on this. That means that at each time at rate 1, an individual in the population will sample somebody else and adopt their type. They can sample themselves as well. That's okay. But they adopt their type. That's what the first step is. Okay. And then this is a result from population genetics. I'll come to it in a second. I'll write on the board. That's in the next slide. The graph I do is I connect everybody of the same type. Connect all ones and connect all zeros. Okay. So it's a very simple graph. Okay. Each time only the types are changing. Once the types change, the graph reconnects and all type 1s and type 2s.
Could you also do that with a fixed probability P?
Yeah, I will do that. This is the example I'm motivating.
Okay, so you're not doing that with probability 1 and
this is this you think of it as this Graphon like this.
so my question was, can you replace the ones by
Yeah,
by P's or
I will do
Q's
that.
or-
I will do that for sure. I'm just giving an example of how to do this. It's simple. You can do much more. I don't want to go into the details immediately, but this is a key idea. So once you do this, so then what you do is this point right here is the fraction of 1. So it's xn by n. That's what the Graphon will look like at the nth level. So now you know if the xn by n converges to y, which is right Fisher, you're almost there. So you're almost there. So then if you just look at the number of copies of a subgraph f in Gn, it's just going to be xn to up to a constant thing. I made a small error, but yeah, xn to the power k divided by n to the k and n minus that to the n. Yeah, this put tilde. Once I do that, I know from population genetics that this person right here is going to go to my right Fisher, right? This person right here is also going to right Fisher, right? 1 minus that. So then as n goes to infinity, I just get going to this Graphon, this GNT that I have developed as n goes to infinity, all the subgraphs will converge correctly. Subgraph counts converge. I established that this, I can think of this as my TF. H is the.
So what goes wrong with crane?
Maybe I to save my head, I'll go say what goes right with me.
No, it's no. I love you saying what goes wrong with crane.
Yeah, maybe, yeah. There's nothing wrong with crane. It's just a projectionist boundary variation. So it just yeah.
So, but why can't you apply the crane theorem to your example?
Yeah. So what will happen is I'm constructing it at the nth level from the graphs level, right? So I'm not doing the exchangeable array. I'm not giving you complete information, right?
It's not exchangeable, I guess.
It's not exchangeable anymore. Like I'm doing,
Infinite exchangeable.
and I'm not coupling
That's it.
n and n plus 1. My nth level graph is very different from n plus 1 level. No, almost sure coupling. Maybe that's better way. That's what goes wrong with me. So, So the graphon is what? The graphon is like this, right? So like this, and then you have two communities, 1 and 0, and then these guys all are connected to probability 1, and this is the point right here that you have. That's a graphon H. So it's a simple example that shows you how to do it, right? But now once you have it, you're on your way, because once you know your subgraph counts behave like some polynomial of your type space, that polynomial will converge to the polynomial on this side, and that will be the polynomial on the diffusion. Like Remco asked, you can now do anything you want. You can change these people, you can make them time dependent, any way you want. All you're going to end up is the way I've set the thing up, I'll always get a polynomial in the type space. So it's a function of the type space. That's how we have rejigged it. So I played a little trick on you in some sense. I'm not truly creating a graph dynamics. I'm changing the vertex type, and I'm brute force changing lots and lots of edges at each time. The moment the type changes, I'm just zooming on. Everybody gets the sample. So each time I'm changing order n squared edges, formally speaking. That's what saves the day.
So the square root of n squared is n, and you really have to do that, right? Otherwise,
That's right.
you're not going to get any diffusion.
That's right.
What happens to the process if you? So what if you converge to all zeros or all ones?
Converts to all zeros. Yeah, this will have no equilibrium. It'll just go to all zeros all ones.
I see.
The y will hit 0 or 1, and that's it.
And then you just are left with the complete graph, and then you stay there.
That's right. That's right. There's no equilibrium. That's very good. That's very problem.
Thanks.
I think this is an important point. Everybody's asked us. Do you have a non-trivial equilibrium state for this process? Do you have an example of a non-equilibrium state? You can get artificial ones, but a truly non-constant equilibrium. That's an interesting question, I think. I don't think we have a good natural example. We have many artificial examples, but not natural. That's it. That's the graphon. So now you can make alpha, beta, delta like you want. Just the same polynomial will work, same construction will work. So there's a theory to be set up. So I've given you how the subgraph counts converge. If you want the process to converge, you have to set up the theory correctly. Because all I showed you a proof was that the subgraph counts at time s goes to subgraph count limit. But I want a diffusion in this space as a weak convergence of these processes. So to set up the theory properly. But you're lucky because the subgraph counts are kind of moments of the graphon space. You can work with them. So you'd establish so one dimensional will give you the proof that I gave you will give you the one dimensional convergence. You would establish a tightness criteria in graphon space. And once you do that, you have to obtain process convergence. So the theory you have to set up. That's what we did in our first work. Too small. So we have this theorem that we have equivalent conditions that's graphons going to graphon in D0 infinity on graphon space is the same as these moments converging, is the same as the mean of the moments converging. This is a sort of a theorem available for everybody to use right now. Don't need to do any coupling, no exchangeability. Just look at the subgraph counts, take the moments, you're on your way. Process will converge. This criteria is set up for everybody to use, and you can use it. This was going to be my talk at the Urandom meeting before the pandemic. So that's where we were. So then we started discussing a little bit more after that. So I'll go quickly tell you after that. So now you can do many more things. You don't have to do one type. You can do multi-type models. So there are 3 types, and you have different connections to each type. They can vary with time. You can do the same construction that I did to get you the answer. Right? So instead of xn being 0, 1, you can say 0, 1, 2. Then you have a 3 by 3. Then sit with us who's working in population genetics for a long time. The next thing you do is you take M to infinity and you can do the Fleming VO. So you get a continuous steady limits. And then it's not a finite block, stochastic block model graphon anymore. You have a cool graphon that moves around. Get height to the But there's still something disappointing about this whole thing. Or not disappointing, anticlimactic. Because everybody is a function of the type space. In some sense, we're sort of playing a trick. Everybody, once I give you the type space, the edges are determined in some sense. So everybody is a one measurable function of the type. It's truly not that that you'd like a model in which the edges interact with the vertices and the vertices interact with the edges and there's feedback either way. Here, the moment I give you the vertex types, the graph is determined in some sense. For instance, up to a certain randomness.
Right, but when you had the stochastic block model,
So things, they are not deterministic, right? Because delta, eta, and beta.
I said up to that edge probability, you're right. But the moment I give you delta, eta, and gamma, and the types, the graph is determined. Right?
Sure, but that's sort of true for stochastic, just true for the standard stochastic block model as well.
Yeah, next example. It's correct, but it's a little bit. I'll tell you an example that I have in mind, and then maybe my comment will become more clear what I'm trying to say. See, so for example, the edges don't change the types. The types move on by themselves, and given the types, the edges are given to you. But the edges don't interfere with how the types are moving. That's what I meant by saying that the graphon is given. My comment is clear. I'll come to it in a second. This is work in progress. So from now on, whatever I say may or may not be true in the last 5 minutes. The co-authors will confirm if it's true. So what I want to do is, what we want to do was that the vertices will do a Wörter model on the existing graph at that time. Okay, so whatever the vertices looking at the time, we'll do a Wörter model. And then every now and then the edge also will flip, depending on how the vertices. So now, what all we'll have a vertex like. Let me use let's say let me use something else. Let me use green for 1. Let me use orange for 0. Okay. That means all my edges will look like. Let's see, there'll be 3 types, right? All my edges will look like either an orange and an orange, or a green and a green, or a green and orange. That's how my edges are going to look like. So now what I can do is I can make my edge dynamics. I can make my vertices move in some way, right? So my vertices will move like Wörter model. That's one dynamics happening. And my edges will move depending on how the vertices are. They'll also flip on and off depending on the vertices. The idea is clear. So now I can't do what I did before. I don't have independence. I can't average out I do the subgraph I can't compare it to the mean concentration and get the thing. That's not what happened because I have this confusion now. There's feedback. This model has been studied. People have studied coalescence time of the opinions on this model. I think Riddhi Basu and Alan Fly have a paper on that. But that's on the Wörter model. You don't worry about what's happening to the graph. Graph will do something. But this is a classical dense graph regime you'd like to resolve, right? You'd like to know. Mildly put, the idea is very simple. Your number of edges flips is the same as the total number of types. It's easy to see. And the vertex changes are proportional degree. I think it should be 0, 1. I'm not sure. I don't know why I put plus minus 1. So what are the challenges here? So first challenge is you can't use the old idea. You can't concentrate on the mean and show use heuristic and get the whole thing. That's going to be hard to do because your edges are going to interact with the vertices. So if you just go look at the generator of this Graphon process. So the nth level, you can write a generator down. So it looks hideous, but it's not so bad. See, what am I doing here? Here, let me do the mother color, maybe purple, maybe brown. So here, I'm just doing the vertex flips. Okay, so vertex are flipping at rate eta. So that VLI is how the vertex is flipped from a green to a red or a red to a blue. So let me just copy this down so it's clear. So what's happening in these two terms is that this person right here is measuring the discordant zeros. Or these guys. Right? These guys are measuring the concordant ones. This one is this one. All these guys are flipping.
So is that the number of such edges?
Which one?
I mean, either the SD or the SC.
SC is just a rate. It's a rate. It's a generator, right? It's a generator.
Okay.
There's a rate at which these are flipped. This is how you can write generator down after you write the simple calculation. Or you have a generator, you just take n infinity and see what happens, right? Converge or not converge. If it converges, you're in good shape. You have a measurable, you have a generator on Graphon space. And if that's second order terms, then you have a diffusion and you're on your way. So Adrian did the simulation of this process. You look at the fraction of zeros in the population. They look quite diffusive. They don't look they're all like a deterministic process. There's a nice diffusion happening. That's clear because the water model is going to the Fisher, right? And then you have a diffusion coming in. That shouldn't be a surprise. The next slide is a surprise. So maybe I'll give you a half a second to think about what is happening to the edges. Right? The edges are flipping depending on how they have concordant opinions or discordant opinions. They're turning off and on with that. Right? So it's quite cool. The total edges are deterministic in some sense. That's what the black line says. Okay. But each individual color ones are diffusing. It's not expected after a while to think about it, but what's going on.
You're saying deterministic, but it does seem to be moving. That's not a random curve. It's of bounded variation.
That's what it seems. But I'm sorry, I take it back. That's all I meant. I meant one bounded.
Okay.
I don't think it's a non-bounded. Sorry, it's not diffusive. That's all I'm saying. There's nothing more. Then, so what you need to do is to, so this proof is coming up together slowly. Lots of stumbling blocks around, but broadly among friends, you need a subgraph, colored subgraph theory to come about because you need to look at graphs with colors and shows colored subgraph counts converge to colored graphons, and that's not too hard. It's available more or less around. You have to work out the nth level generator, and what happens is that the trick is that what will happen is you'll have a bunch of terms multiplied by n. In the generator and bunch of nice terms here. Let's put nice, which will be the true generator of the process. So what you do is you think of this as your manifold on Graphon space. Whatever you make sure your Graphons are all in the space where this term vanishes. So that's I'll just call it as so make it 0 and rush into manifolds. Make it 0 and process to rush into manifold. So the process will spend very little time outside this manifold as n gets larger and larger, and it will go to the manifold, and only this part will remain. That's the form. That's what you have to show. If you can show that, then you know that there's amazing topology available to you to show that the process converges. This is the thing. So if you have authors like Adrian who will do the work, this huge generator, he'll calculate and get the whole answer down, and then this is something we'd like help on. The manifold is the top line, and the bottom is the limiting generator, formally speaking. So manifold is actually like this. It's a very nice Graphon set. So it's what we called as tadpoles. I don't know if that's a common terminology in Graphon theory. So we need to understand the following. So I have some subgraph that I have in mind. I pick a vertex, let's say it's green. I'm going to attach another edge. So what this edge will do is it will do one of two possibilities. On the left-hand side, let me go here. On the left-hand side, it will attach itself. Copy this. On the left-hand side, it will attach itself. I think it'll change its color to orange, and then adapt the vertex color and become green. On the other one, it will go attach itself and become an orange. So, and this process is what we have. We take a graph, a finite graph, and do this process. We need these two counts to be the same. We think this might classify all Graphons, but we don't know that. If it does, then you're on business. I said correctly, right? I think so.
So this is basically saying ignore the colors. If you were to know the subgraph counts of all the graphs with one edge sticking out, does that uniquely identify the Graphon? That's your question.
I think so. Yes. If that's available to us, then
That's
the
a good
manifold is
question.
ready. Otherwise, it's some artificial condition. Again, grand claims. I think this is the first example of where the vertices interact with the edges, and edges interact with vertices. I don't think that's been done ever. We don't use any moment closure or mean field approximation. It's brute force computation. I think it's a rich class of models. It's very exciting.
Thank you very much, Siva, for this exciting talk. Are there any further questions?
So I know, of course, you've just started exploring this, but for instance, in the Graphon case, the limit Graphon really helped get things that you couldn't easily get in the pre-limit. Right. So here, is there a similar?
It's again a little anticlimactic. I'll tell you what the limiting Graphon will be. So you have a. I mean, just think a little bit. There are only two types, zeros and ones, right?
Yeah.
So you're going to get a stochastic block model, right? That's easy to see, right? So all that remains is to estimate what these guys are, and what this point is, right? So under those SCs that I mentioned before, under some specific ratios of SC, you will have an equivalent distribution for the edges, and they will appear here in the alpha beta delta. And the whole thing comes down to what this guy is going to look like. If you believe my tadpole calculation, this will just be a function of the color vertex. And function also is explicit. You can write the function. So it's kind of anticlimactic. The Graphon is stochastic block model after all this hard work.
Very interesting talk. So I was wondering, so this setting is only working, only work for block models where I can characterize the block structure by a finite number of parameters?
No, no, we have this Fleming-View process that works quite well, I think. So the Fleming-View is like a sort of a not stochastic block model.
So it's very general.
Yeah, it's very general. You can have height varying as well. You can do very things, but it's a function of the type space.
Mm-hmm. So my other sort of, I mean, I want to understand this, but I have some sort of confusion. We have a graph start with, and then there's a process on it. And then the evolution is not in terms of the graph, it's in terms some of the aggregate property of the graph. So we want to understand that rather than directly understanding the evolution of the graphs. I just want to know if
Yeah,
I'm
I think
correct.
that's all the interesting examples. I think I agree.
I see.
I don't think technically. We can say I think technically we are just learning. Correct. That's a good thing to understand.
What is special about the graph with a edge sticking out?
That's what the manifold is. The nth term in the generator, the manifold looks like that. The two tadpoles are the same, or counts the same.
Yeah, so I guess